Hi all. Our last class was based on the fundamentals of reciprocating pumps, and today we shall discuss about the acceleration head. The piston is moving to and fro inside the cylinder of a reciprocating pump. So the piston is under acceleration and retardation, and the flow of water to the cylinder is by the movement of the piston. So any change in velocity of piston, that is acceleration or retardation of piston, will affect the flow of water through the suction and delivery pipes. So that imparts a head, pressure head. It is called as the acceleration head. So we assume that the piston is starting from the extreme left. So it is starting from rest, it is moving towards right. So first of all, as it is from rest, it is under acceleration. Then at the end of the stroke, the piston stops at the extreme right point. So at the end of the stroke, the piston is under retardation. So during the suction stroke, during the first half, it is under acceleration, and for the next half, it is under retardation. And the same thing happens in the delivery stroke too. So the movement of the piston will affect the flow of water in the pipes, because the water is flowing through the pipes. It is flowing through the suction pipe and it enters the cylinder, and that is only because of the movement of the piston. And the same piston is pushing the water to the delivery pipe. So any change in velocity of piston will affect the velocity of water in the pipes. That is, when the piston is under acceleration, the water flowing through the suction pipe also will be under acceleration. Same thing for delivery pipe too. And if the piston is under retardation, the water in the suction and delivery pipes will be under retardation. So it is under acceleration and retardation, means the velocity is not constant. So this effect varies the velocity of water in the suction and delivery pipes. Any change in velocity will vary the discharge, so the discharge is also varied. And this creates a pressure head, and this changes the pressure inside the cylinder, and that pressure head is called as the acceleration head. So that figure gives the movement of the piston from left to right. So x is the displacement of the piston inside the cylinder, and that is happening in a time t. And at the same time t, the crank moves from A to E. So A was the initial position of the crank. By the same time t, it is moving from A to E, and its angular velocity is omega. The angular displacement is theta, and the same distance x can be drawn here as AF. AF is x, OE is R, OE is the radius of the crank R, and capital A is the area of the cylinder, small a is the area of the pipe, suction or delivery. Take it as common, area of the pipe. L is the length of the pipe, suction or delivery. R is the radius of the crank. So when the crank is at A, the piston is at extreme left. When the crank is at B, the piston is at the exact center of the cylinder. When the crank is at C, the piston is at the extreme right. Then it moves into a delivery stroke. When D is at the middle of the delivery stroke, and when it reaches A, it comes to the extreme left. Now, this angular displacement theta will be equal to omega t. Omega is the angular velocity, angular speed, t is the time, so omega t. And you just look at the triangle. This FO will be r cos theta. FO is r cos theta. So this AF is x, FO is r cos theta. Now this x is equal to distance AF, that is AO minus FO. AO is r, FO is r cos theta. So x is equal to r minus r cos theta, and theta is omega t, r minus r cos omega t. So that is the distance traveled by the piston, displacement of the piston. Now for getting the velocity of the piston, differentiate it. V is dx by dt, velocity of the piston capital V, dx by dt, d by dt of r minus r cos omega t, that is omega r sin omega t. That is the velocity of the piston. Now you apply the continuity equation between the suction pipe and the cylinder. That is, area into velocity is a constant. That is, area of the suction pipe into velocity of water in the pipe is equal to area of the cylinder into velocity of water in the cylinder. A1 V1 equal to A2 V2. So for inside the cylinder you take capital A, capital B. For the pipe you take small a, small b. So capital V into A equal to small v into A. Therefore, the velocity of the water in the pipe small v is A by A into capital B. And already we got capital V omega r sin omega t. So A by A omega r sin omega t. That is velocity. Now the acceleration is dv by dt. Don't put acceleration as a because already we have taken a as the area of the pipe. So acceleration dv by dt, d by dt of a by a omega r sin omega t. So acceleration is a by a omega square r cos omega t. Now the mass of water is density into volume. The volume of the pipe is mass of water in the pipe. Volume of the pipe is length L, area A, so AL. So rho AL is the mass of water in the pipe. Now the force required to accelerate the water in the pipe, that is mass into acceleration. The force required to accelerate the water, mass of water into acceleration of water. Rho AL, A by A, omega square R cos omega t. A will be cancelled. Rho L, A, omega square R cos omega t. Now the intensity of pressure due to acceleration. Intensity of pressure is force by area. Again, you divide by area of the pipe. For the force, so rho A by A omega square R cos omega t. Force by area. Now the pressure head due to acceleration. The pressure head due to acceleration is the intensity of pressure divided by rho g. You know, P equal to rho gh. So H is P by rho g. Intensity of pressure by rho g. The intensity is rho g. So that equation divided by rho g. So the pressure head due to acceleration HA is L by G A by A omega square R cos theta. Omega t you write as theta. Omega square R cos theta. And if you take suction and delivery pipe separately, for suction pipe you put the suffix S, delivery pipe you put the suffix D. So the pressure, acceleration head in the suction pipe HAS, LS by G, A by AS, omega square R cos theta. The acceleration head in the delivery pipe HAD, LD by G, A by AD, omega square R cos theta. So this derivation is very important. This will be useful in coming discussions, and there can be problems based on this. It is very important. Now, this change in velocity will affect the friction in suction and delivery pipes. You know the loss of head due to friction for FL V square by 2 GD. So the one term is velocity. So any change in velocity, the variation of velocity will affect the friction head, the loss of head due to friction. That is Darcy-Weisbach equation. Now, from the previous derivation, the velocity of water in the suction or delivery pipe V is A by A omega square omega r sin theta, and you substitute that V here. So V square you A by A omega r sin theta the whole square, that is HF, the loss of head due to friction in the pipe. When you apply for the suction pipe, you put suffix S HFS for FL less 2G ds A by AS omega r sin theta the whole square. Similarly, delivery pipe HFT for FLD 2G dd A by AD omega r sin theta the whole square. That's all.